Hey, so I've actually had quite a number of lingering these fundamental questions on what Hamiltonians really are, why they're even the mathematical tool to describe the energy of a quantum system, and how the hell they dictate the time evolution of that system. Because those two different things came across to me as quite different counterintuitive things that the Hamiltonian all serves, but I didn't understand how or why. Um, like just to think of the classical case, if I gave you a ruler and told you that this ruler measures the energy, or let's say the state of a given system, and at the same time, the ruler told you how the state evolves through the system. So it tells you how a given particle starting at 2 centimeters would move throughout the ruler. Those two different notions seem very different to me. But they're actually superficially different, but they're actually the same, which really surprised me. And that's what I want to kind of share in this video, why that's actually obvious. So yeah, so I think one important part to distinguish is what even is a measurement operator, right? So in a classical sense, we take advantage of the fact that measurement comes so easy to us. If you flip a coin and it lands heads, it's heads, right? But if you're talking about an irreducible linear combination of heads and tails added on with complex amplitudes, how do you describe, what does measurement mean there? Like what is measurement? And one way to go about it, one way to go about it, and most of what measurement is actually projections onto a measurement axis. So if you're talking about some alignment of an electron spin, or if you're talking about an alignment of some quantum particle with a uniform electric field, then what you're describing is the projection of that vector, that which you can represent the quantum particle as a vector, onto that onto that uniform electric field. So you can see how, depending on our definition of energy, which I'll come to afterwards, we can actually make this operator. We can make this operator a projection onto some measurement axis. And if we have some quantum state, which is described by a state vector in a Hilbert space, and we want to describe some notion of energy to this quantum state, we could describe, in a sense, a measurement axis, just like any other. And this measurement axis, in this case, would be the measurement axis for energy. And it turns out that any projection is also a Hermitian matrix. And why not call that a Hamiltonian? Because a Hamiltonian is, by definition, a Hermitian matrix that gives you the sum of the kinetic and potential energies of a given quantum particle in the system. But that's what it is, right? That's kind of what we concluded, that you have any kind of quantum state that's described by a state vector. And just like you have your computational basis states, which draw orthogonal axes, which draw orthogonal states for it to span the whole Hilbert space, you can also have a series of measurement axes. And these measurement axes can lie in different directions that characterize how energetic a given quantum state is. So you could say if the electron's pointing this way, it's like super not aligned with a uniform electric field, while if it's pointing this way, it is aligned. And you could extend this even to the Hubbard model, which is like, are bosons or fermions in a lattice in the most energetically favorable position, such that it's not adding more potential energies. But I don't want to get into that. So yeah, so Hamiltonian, we kind of understand that it's an energy measurement operator. Okay, but what is the implication of that? Well, what that means is that if a given operator, if I give you a certain operator and it tells you the energy of a certain state within that system at any given point in time, that basically paints an energy landscape, right? It tells you what is the energy of any state throughout time. And so any state in the Hilbert space, it ascribes a certain energy to. And that seems kind of peculiar, right? Because, at least to me, this might be naive, but I intuitively thought that energy is inherent to a particle. But what kind of struck me as profound, and this, correct me if I'm wrong, but I kind of understood the environment as having a broader role, as having a more definitive role in defining what energy actually means for a given system and not the quantum particle itself. So by describing an environment as a Hamiltonian, that basically describes how do you measure energy within the system. So knowing what the Hamiltonian is basically knowing what is what is energy? What does energy mean for such a system? And that's what the Hamiltonian is, because it explicitly defines the energy landscape as we talked about before. And how this ties back with the system's time evolution, as we want to initially discuss, is the second law of thermodynamics. And the fact that if you don't know the second law of thermodynamics, you could just think of it as all systems tend to naturally converge to their lowest energy state, or the state at which it's at most at ease. So if we have this certain operator that describes the energy of a given system, it would be quite natural to assume that now all systems tend to the lowest energy state. So then you could, in a sense, say that this operator, that the definition of energy for the system is actually governing the evolution of that system throughout time. And that's why the Hamiltonians are so powerful and sit at the bedrock of quantum mechanics, as Schrodinger's equation exactly entails all of this. I'm just kind of conceptually explaining Schrodinger's equation here. Um, Hamiltonians tell you everything about a given state, and its evolution once you give it the initial state, because Hamiltonians actually describe the energy and how to define energy. And once you define energy, you can once you define the energy landscape and you figure out where your initial state is, the ball's just going to roll down the hill, in a simplistic sense, right? So yeah, that's how I kind of connected the dots between, at least that's how I started to think about and reconcile the Hamiltonian's role as encoding the dynamics of the quantum system, the time evolution, but also as an energy measurement operator, which is right. And one thing I actually forgot to add is that these measurement operators are projective measurements, and projective measurements are projectors. And by definition, projectors are idempotent, which implies that if you apply a projector twice, you get the same projection operator, which makes sense because if you're projecting a certain vector onto a certain given field, and then you project that vector again with another projector, you're going to get the same vector again. So basically, these measurement operators are projectors, and projectors turn out to be Hermitian because if you take the conjugate transpose, you're just going to switch around the cat and the bra, and you're going to get the same thing again. So you can see why Hamiltonians have to be this kind of measurement, right? If you define some certain energy axis, if you define some certain measurement axis and say that those measurement axes are now characterizations of the energy of a quantum state, then to measure the energy of any state in that system, you have to project that state onto that axis. And in doing so, the mathematical tool to accomplish such a task is a projector, which is Hermitian, which then let's call it a Hamiltonian, because I forget why it's called a Hamiltonian, but that's kind of the intuition why Hamiltonians have to exist in describing the energy of a quantum system. So yeah, that kind of connects, I think, the two initial interpretations of the Hamiltonian, and should make it clear why these two following descriptions kind of entail the same thing, right? So if one says the system's evolution is governed under X Hamiltonian, or if another says the system's energy is described by the expected value of the Hamiltonian measurement, those two entail the same things. So, if you're a mathematician, you'd think, so okay, so energy, okay, all these examples, Pawan, that you've given me, they're strictly physically inspired. But could we extend these notions beyond such systems? Why are we talking about electric fields and bosons and lattices and what would happen if we extend this notion of measurement into, let's say, a graph theoretical sense? Say I have a graph theory problem, say max cut. Um, if you don't know what max cut is, don't worry about this portion. But say you have this mathematically theoretical problem. um, could you use a Hamiltonian to describe the validity of a solution of a given system? And yes, you can, because if we use a broader definition of energy, which we described earlier, which is the degree to which a system is at ease, that very naturally lends itself into a theoretical problem, and we need not relegate these mathematicians churlishly as not being physically inspired these problems, but they're almost as justified as these actual physical problems, because what even is energy, right? So in our physical problem, we define energy as, let's say, the alignment on a certain field, or just generally the degree of ease of a given system. And in the same sense, in a graph theoretical problem, once we define the problem, we can say that the validity of a given solution to the graph theoretical, the validity of a proposed solution to the graph theoretical problem could also be described as the energy, right? So that's the energy of that system. So then you could very easily extend this notion onto systems that are not physically inspired. And that's where the max cut Hamiltonian comes in, which basically just measures the number of edges which contains nodes of two different colors. And it promotes that. It's energetically favorable to have two nodes of two different colors at each edge, as indicated by this negative sign. And that's what's so beautiful about these Hamiltonians, because you can just glance at them, and just by looking at the signs, you can understand the dynamics, the interplay, the forces that are pushing this quantum system from, yeah, the energetic evolution of this quantum system. So here I have the Hubbard Hamiltonian, and I'm not going to go into this too much because my article covers this perfectly. At least what I think is good. But yeah, this term right here describes the tunneling term, which promotes the tunneling, the hopping of quantum particles between different sites of a lattice. And this term right here kind of it acts as a force against that by the plus sign, and specifically it acts as a force against two such quantum particles occupying a single site. But but yeah, the you need not understand if that seems all jargon to you. You can throw that out the window. But the core message here is that these Hamiltonians are a fundamental and irreplaceable mathematical tool to describe not only the evolution of a quantum system, no, to describe the energy, the description, the characterization of energy of a given quantum system, and thereby dictate the time evolution of that quantum system. So, yeah, measurement is the problem itself, and at least what I feel is that the rules you carry to distinguish the degree to which a system is at ease deceivingly encodes the dynamics of the system that is being described. So yeah, I hope that clears some questions up for other people that may have similar doubts or queries. Yeah.